So last time we did a lot of math about cyclic groups, and the point was just to understand the small subgroup problem and how it's not enough just to pick a large prime when you're doing Dippy-Hellman key exchange. You have to pick a big safe prime, and that stops there from being lots of small subgroups, and it also makes it easier to pick a generator. So today we're gonna talk about attacks on discrete logarithm problems. Some of them are applicable to the discrete logarithm problem over any group, and what have I done here? So I want to make a new one of these. Actually, when I did this last time, I wasn't able to write afterwards. Okay, that's good. All right, so the discrete logarithm problem. So it makes sense over any group. So if you've got a group, you know, it's okay if you just want to keep thinking of G as like ZP star or N star or something. So those are definitely the most important cases, but there are others like elliptic curve groups. So G is any group, and it's a cyclic group. And the book likes to use alpha as a generator, so I'll do that here. So alpha is a generator. Anybody want to say what that means?
You mean alpha?
Yeah, what does it mean to be a generator?
I don't know what the answer to that is.
Okay. It means for any G in G, there is some integer x, and x is just something between 0 and the cardinality of the group, so that alpha to the x is equal to G.
So it generates that all the numbers in that group.
Yeah, exactly. So if you just look at the powers of alpha, it generates the entire group. So if I write alpha 0, alpha 1, alpha 2, blah, 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 all the way out to alpha cardinality of G, there's just going to be a repeat here, because this is going to be the identity element, which I'll call 1. And this is also going to be the identity element. So it kind of loops around. But this, as a set, this will be equal just to the group. So every element of the group is x is alpha to some power, and that is the discrete. Sorry. And the discrete logarithm problem is given G, an element of the group, what is x? So it's asking what is the x so that alpha to the x is equal to G. Sometimes this x is called the index of G. And for some groups, the discrete logarithm problem is hard, like in ZP star. So this is the group that you kind of generically use here, but you can also use elliptic curve groups. And then in other groups, the discrete logarithm problem is not hard at all, like in ZP with no star. So this is the additive group, and the discrete logarithm problem, if you express it in additive notation, it's just saying that x times n, or sorry, x times G is equal to, x times alpha is equal to G. And then the answer is just x equals alpha inverse times G. So in the in ZP with no star, then the discrete logarithm problem is totally easy. So now I'm going to go through the part of chapter 8 that is attacks on the discrete logarithm problem. Okay. So first there's just brute force. So you can just look for every possible x. So how many x's could there be? There could be the cardinality of g x's. So you want that to be a space that's too big for anybody to ever search through. And so you need that to be at least 2 to the 80. So you need a pretty big group. We'll see that we're actually going to work with groups that are much, much bigger than that. So if you're working with ZP star, so it turns out that ZP star needs to have a prime that's like thousands of bits. But to avoid brute force, all you would need is p minus 1 greater than 2 to the 80. That would stop brute force. The second thing that we're going to look at is called Shanks. I think it's Shanks's, or is it Shanks? I don't know. Baby step, giant step algorithm. Don't ask me why they decided on this name. I will show you the baby step and the giant step, but when I do it, I get no, metaphorical connection with babies and giants happening in my brain. So just to fix the notation here, we're gonna, beta is equal to alpha to the x. And of course, what we want to do here is find x. Okay. So this approach that Shanks came up with works against any group. So what you do is you write x is equal to xg m plus xb. So what are these three numbers? They're just made up numbers. M is a constant, which is the ceiling of the square root of the cardinality of g. So these, if you guys seen ceiling before, it just means round up. Because when you take the square root of a number, like the square root of 7 or something is going to be a decimal. The square root of 7 is like 2 point something, but then when you round up, it becomes 3. So the ceiling is just saying round up. And this x and this g are just some numbers in the range. So xg and xb are just numbers in the range from 0 to m. And so, there's nothing special about x. Any number, any number can be expressed this way. And I'll do an example in a minute. But notice that you, so what is x? X is something in the range from 0 to the cardinality of g. So can you really express enough numbers using this form? You can, because both m and xg are basically the square root of g. So when you multiply them together, what you get is something pretty close to the cardinality of g. And then if you're a little bit short, then you can add an xb here to make up the difference. So this is just an odd way of representing a number that some smart person came up with. All right.
So, Professor, isn't beta equal to alpha x same as g is equal to alpha x?
Yes, yeah, I'm just following the book's notation. I was using G for group element, but for whatever reason, the book uses beta. So I switched to beta.
Okay.
But it's the same as G. Okay, so beta is equal to alpha to the x. So if we make this substitution here, we can write beta is equal to alpha to the xgm plus xb. And now we're just going to rearrange things here. None of this is really going to make any sense until we get to the example, but just check my derivation and make sure I don't do anything wrong. So over here on the right, this becomes alpha to the xgm times alpha to the xb. That's just the way exponents work. So we've got beta here. And so now I'm going to move this one from the right over to the left. So that means I multiply both sides by its inverse. So on this side now I have beta times alpha to the minus xgm is equal to alpha to the xb. This, by the way, B is for baby and G is for giant. So here's baby X and here's giant X. Okay, so it'll turn out to be just a little bit more computationally efficient if I rewrite that thing on the left as beta times alpha to the minus m to the xg is equal to alpha to the xb. And the reason is that we're going to be checking lots of xb's and xg's. So now this will just be some fixed number, and we don't have to do an inversion every time we try a different xg. We just take this number, whatever it is, and raise it to the xg power. Okay, so the basic idea here is to step one, the baby step, is to build a table of, alpha to the xb for all possible baby x. So, so baby x can take on all of these values. So this requires basically the square root of the cardinality of G space, because you have to store the table. And it also takes that much time, because you have to, there's one step for every possible baby X. So it's the square root of the cardinality in space and time. Okay, now what you've done here is you've come up with like kind of a vector here, and it's all the possible right-hand sides of this equation. Now what you do is you try all the giant X one after another. So every time you try a different giant X, it's going to be something that might be in this table. And eventually you'll come to something that is in this table, because this equation is true for some choice of baby X and giant X. It's true for the choice of giant X and baby X that make this equation true. So there's some XG and XB here. And when you find the right XG, what will happen is you'll get a hit for an entry in the table. Okay, so let me write that down. So now step two. The giant step is to try each XG and look for a hit in the baby table. So what does a hit mean? It means that beta times alpha to the minus m to the xg is in the baby table. And it eventually will be. So when that happens, then you have xg, but then the index that matched on the baby table also tells you xb. And so once you know xg and xb, you can just write down x, because x is equal to m times xg plus xb, and you're done. And so the time and space of the overall attack, so it took big O of the square root of the cardinality of G to build the baby table. And this is also how long it takes to look through the baby table. So you have big O of square root of the cardinality of G to build the table, plus the square root of the cardinality of G to look through the table. And so that factor of 2 doesn't matter in terms of big O notation. So the total time is proportional to the square root of the cardinality of G. So in terms of bits, so with brute force, we had said that it was necessary that the cardinality of G was at least 2 to the 80. But what we've just found is that that's actually not adequate, because we can actually crack the discrete logarithm problem in time proportional to the square root of the cardinality of G. So we actually need this number to be bigger than 2 to the 80. So that was optimistic. And so this means that the cardinality of G has to be bigger than 2 to the 160 to avoid the baby step, giant step algorithm. So it forces the system to have twice as many bits as it would otherwise. So let's do an example with some real numbers. I'm going to do G equals Z71 star. And it turns out that alpha equals 7 is a generator for this group. And I just make up a target x. I made x equals 49. Okay. Okay, and so that forces beta. So beta is alpha to the x, and this just happens to be, if you do 7 to the 49th power mod 71, is that what we are doing here?
Yeah.
Then that turns out to be equal to 17. Okay, so alpha is 7, x is 49, beta is 17. So first let's make the baby table. So I'll write down all the possible baby x right here. And so this is going to be 7 to the xb mod 71. So I did this earlier using Python. Oh yeah, so what is m here? M is the ceiling of the square root of the cardinality of this. The cardinality of this is 70. So it's the, so that turns out to be 9. So I have to try 9 values for x b here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and so now I'm doing 7 to each one of those here. So 7 to the 1 is 7, 7 squared is 49. And then using a calculator, I found these other values. They are 59, 58, 51, 2, 14, 27, and 47. Okay.
So can you repeat how do you got it 70?
Yes, because the cardinality of ZP star is always P minus 1. Because this is,
Okay.
yeah, so ZP star,
Thank you.
yeah, ZP star is equal to 1, 2, 3, up to P minus 1. Okay.
Okay.
So that's the baby step. And I think I might like to take the baby table and go work on a different page. Let's see if I can manage to do that. I probably actually have room. Okay, I'll just take it down here to some less busy place. So there's the baby table, and now with the so remember what we're doing here. We have beta times alpha to the minus m xg. That sounds good, Gibran. What are you having?
Oh, my fault. I thought I was on mute. Nothing. Just cereal and milk.
So here we have alpha to the xb. And so we just made a table of alpha to the xb. That's what the baby table is. And now we need to start evaluating these and then try to find a match in the table. So we already computed beta in this example is equal to 17. And it turns out that alpha to the minus m, how do we do that? So first we need, that's the same thing as 7 to the minus m. So first I figure out 7 inverse in this group, and 7 inverse turns out to be 61. And then I raise both sides to the m power here, which is the 9th power. And so that gives me 7 to the minus 9 is equal to 61 to the 9th power, which in this group is 68. Okay, so now what I'm computing to make the giant table is beta is 17. So what I'm doing is just filling in the blanks here. So this is 17 times 68 to the xg for a bunch of different xg's. And let me just copy the result over here. So we'll make one column is 17 times 68 to the xg, and over here is all the possible, whoa, that's not very straight. Over here is all the possible xg's. So there's just 9 of those like before. 1, 2, 3, 4, 5, 6, 7, 8, 9. And these numbers turn out to be 20, 11, 38, 28, 58, 39, 25, 67, and 12. Okay, and now we're looking for a match. So do you see anything that's in the giant table that's also in the baby table?
No, I mean there's for the value of 5 in xg it's 58, and the value of 4 for xb it's 58. But
Yeah, that's right. That's it. So so what we get is this this equality is true. This equality is true when xg is equal to 5 and xb is equal to 4. Okay, and we
okay.
we know that m is 9, so now we can just write down x. X is equal to 9 times 5 plus 4. This is m times xg plus xb. And so it turns out to be equal to 49. And that's exactly right. We picked x to be that at the beginning of the problem. So we had, 70, we should have had to look through 70 possibilities to do brute force, but instead of looking through 70 possibilities, we just looked through the square root of that twice, which was much, much faster. Any questions on baby step, giant step? Okay, great. So just following along in the chapter, the next topic is Pollard's row. And we don't have time to study this, but I'll just say it's kind of like baby step, giant step, but it doesn't have the big memory requirements. So for a baby step, giant step, you had to store at least this table in memory, which could be large if G is big, but Pollard's row avoids that. So no big space requirement. Okay, and let's go to the next page. All right, so the next algorithm they discuss is Polig-Hellman. And we will not go through the mathematics of this in detail either, but this requires on being able, this depends on being able to factor the cardinality of G. So, every number has some prime factorization. So does the cardinality of G. So E2 ... PL e to the L. Those are supposed to be L's. So this uses the Chinese remainder theorem, which we talked about kind of a simplified version of the Chinese remainder theorem. So we wanted to do a modular exponentiation, mod n, where n was equal to p times q. And rather than working in the big space zpq star, we were able to solve the problem in ZP star, and then solve the problem in ZQ star, and then combine them to get the answer back in the big group ZPQ star. So that is with 2 primes, P and Q, but the Chinese remainder theorem is much more general, and it can handle sort of any factorization here. And so the basic idea is that you solve the discrete logarithm problem in ZPI EI star for, you know, I equals 1 to up to L, and then you can do that pretty quickly, and then combine those results somehow to get back to a solution to the discrete logarithm problem in the original group. And the consequence here is that the biggest, sorry. The smallest prime factor of the cardinality of G should be at least 2 to the 160. So you can use Pollard's rho in each of these problems. So in each of these problems, you still need 160 bits. And then saying that the smallest prime needs to be that big, I think, is just conservative, because you don't want, I guess you don't want the enemy to have any information about the solution. It seems like if the biggest prime factor were that big, then that would help. But I haven't been through it in detail, so I'm just going to trust the book here. The smallest prime factor needs to be big. So if you have a group and its cardinality has a small prime factor, that's bad. Something is kind of funny, like here we're doing everything in all this generality. We're writing G instead of just writing ZP star, because there's this other possible thing that the group could be, which is elliptic curve groups. And in elliptic curve groups, just figuring out the cardinality of the group is hard. For elliptic curves, this attack has a couple of extra problems. One is that they have to factor the cardinality, which might not be easy, you know, because this could be a fairly huge number. But on the other hand, you know, we can factor things out to, like, you know, thousands of, you know, anything less than 1,000 bits probably we can factor. So as long as the cardinality of G is at least 1,000 bits, it's not factorable. But for things like 256 bits, it would be factorable. And we know that elliptic curve groups do have sizes that are on the order of 256 bits. So those cardinalities would be factorable. But the problem is that just knowing the cardinality of the group is difficult. And discovering the cardinality of certain elliptic curve groups is like open problems, though it's very difficult. So that saves you a little bit. And then in ZP star, you have to factor P minus 1, which might be extremely hard if P is big. Okay. All right. So the final thing here is the index calculus. So the attacks that we just described above will work on any group. So they work for a sort of generic G. So they work against ZP star and they work against elliptic curve groups. But the index calculus only works on ZP star. And the index calculus, it requires, you need most group elements. How about this? You need a small subset of G such that most elements of G, or many elements of G, can be expressed as products of elements in the subset. So in elliptic curve groups, this is thought not to be true, but in ZP star, you have the small primes. which are sort of perfect for this. So you can take the small prime numbers in ZP star, and then a whole lot of ZP star can be expressed as products of these small primes, and that makes the index calculus go. So it works here, but not on the elliptic curve group as far as anybody knows. And this is what forces the requirement that P is at least 2 to the 1024. And I was looking at the numbers in the book, and they actually, in like 2007, they solved a discrete logarithm problem that was like between 500 and 600 bits. So I would think, and they were, you know, making steady progress on this problem. So I would think that even this is probably not safe. I don't know. I would prefer P greater than 2 to the 2048. So the prime has to be really big, and it's because of the index calculus. So that's the end of our discussion of attacks on the discrete logarithm problem. So we've already seen one algorithm that depends on the discrete logarithm problem for its security, and that was Diffie-Hellman key exchange. And now we're going to, so by the way, Diffie-Hellman key exchange you can do over elliptic curves or over ZP star. When you do it over ZP star, then you need a big prime. So there was a guy named, an Egyptian man named Tahir Algamal. I think he's still alive, actually. And he's, I believe he was a student of either Diffie or Hellman. And in 1985, he proposed a way to use Diffie-Hellman key exchange for a crypto system, for encryption. And that algorithm is called the Algamal Cipher. There's also the Algamal digital signature scheme, which is very dissimilar, but I guess he thought of both. So we're gonna briefly go over the Algamal Cipher. And here's the way it basically works. Let me just start on a new page here. I'll copy this and go to a new page. So step one is to use Diffie-Hellman key exchange to agree on a shared secret. And the book calls this shared secret KM. And KM, they call it KM because it's going to be a key, so they call it K. And then this is going to be the key that encrypts the message, so they call it KM. In my notes, I just call it K, but I think I'll add an M because that is good notation. Everybody remember how Diffie-Hellman key exchange works? We've gone over it twice, and we're going to go over it again in just 1 second. But for now, they agree on a shared secret, which we're going to call on we're going to call KM. So they are the only two people in the world who know KM, provided nobody can break the Diffie-Hellman problem. And the second thing is, if Alice wants to send an encrypted message to Bob, Alice encrypts X as Y is equal to KMX mod P. So this is over CP star for a big prime P. And then transmits Y. Okay, and of course Eve or Oscar or Mallory are going to see Y in transit, but the idea is that they won't have any idea what the shared secret is from their point of view. The shared secret could be potentially any element of this huge group, so any one of 10 to the 1,000 possibilities, and so they can't use brute force to find it because it's so large. And without knowing KM, there's no way to recover X from Y. But when Bob gets y, Bob does know km, and so Bob decrypts y as x equals km inverse x, sorry, km inverse y mod p. And this works because y is just kmx. So what happens if you do km inverse times km times x? This is just x mod p. So it works. So the basic idea is to use Diffie-Hellman key exchange to agree on a secret, and then use that secret as a multiplicative mask to send elements. One thing though is that km can't be used twice. But let's talk about that later. But km can only be used to send one x. So here's an example. Let's do p equals 101, and it turns out that alpha equals 2 is a generator for that group. So here's Alice's part. So this is not the Algamal Protocol, which we'll talk about in a second. This is just sort of a proof of concept here. We're exchanging one message. The protocol is set up to easily exchange multiple messages. So Alice picks secrets, which is supposed to be sort of randomly chosen inside ZP star. They've somehow agreed on P and alpha. And then she computes her public key, which is alpha to the A, and she sends it over to Bob. So I've picked some actual numbers here just for the sake of example. So let's say A is equal to 37. Then capital A is going to be equal to 2 to the 37th, which is 55. So she sends over 55. Of course, this is mod 101. Over here, Bob is doing the same thing. He's picking some secret B in ZP star. And just to give an example, let's suppose Bob picks 41. Then Bob computes his public key, which is 2 to the 41, which is 72. So he transmits 72 over here to Alice. And now they arrive on their shared secret. So the shared secret km is going to be equal to, so it should be b to the a, but for these particular numbers, that is 72, which is Bob's public key, raised to Alice's secret, which is 37, and that turns out to be 75. Meanwhile, Bob is over here doing exactly the same thing, except that he raises Alice's public key to his secret. And so that is 55 to the 41. And that turns out to be congruent to 75 mod 101. So now they both have km. And so now Alice picks some message that she wants to send to Bob. So just for the sake of argument, let's say that Alice picks 22. And then, so she produces y, which is km x mod p, which in this example is 75 times 22 mod p, or mod 101, which turns out to be 34. So she sends 34 over to Bob. Now, once Bob receives 34, he's supposed to decrypt by doing x is equal to km inverse times y mod p. So he needs to know what km inverse is. So km inverse is 75 inverse mod 101, which turns out to be 66. All right, and so finally he just does x equals, let's put a little question mark here, 34 times 66 mod 101. And this turns out to be equal to 22. And so it works. So that's the correct value, because that's what Alice sent. All right, so that's basically the Algamal cipher and an example. Any questions about that? So if this, if you were gonna set up a system for Alice to send multiple messages, like let's say a client to a server might do that, I guess, or vice versa. So Alice will send multiple messages, or maybe you know, many blocks of the same message. Of course, this is too slow to use, you know, for encrypting huge files. But let's say that Alice will send multiple messages, and then Bob will just read them. So this is a pretty, you know, common situation. So this is worth thinking about. Then we said before that you can't repeat the same KM twice. And so why is that? So let's suppose that KM gets reused, right? And we're gonna, you know, it's common in modern cryptography to work under the known plaintext attack assumption, which assumes that the person in the middle, either Oscar or Eve or Mallory, she might know some of the messages. So in this example, suppose that Alice is going to transmit X1 and X2. These are two different messages. She's going to use the same KM both times. And we assume that Eve knows this one, but not that one. So Eve knows X1, but not X2. So she's watching communication between Alice and Bob take place, and so she sees Y1 go by, and Y1 is X1 times KM, and then the programmer who implemented Alice's encryption did something terrible, which is they made it possible for the same message key to be reused. So Y2 also goes by. Y2 is X2 times KM. Okay, so just look at this for a second. Remember, X1 is known. So if you know X1, can anybody think of a way to recover X2? So you can get KM if you just move X1 over in this equation. So Eve knows both Y1 and X1 in this equation because she gets to see Y1 go by on the wire, and she somehow already knew X1. So she can do Y1 times X1 inverse mod P, and then this turns out to exactly be equal to KM. And then once she knows KM, she can do KM inverse times Y2, and that will just be equal to X2 compared to X2 mod P. Okay. All right. So this is, you know, this is the kind of thing that actually tends to cause problems when people use real crypto systems. They reuse a number that they're not supposed to reuse. So this is an example of that. Okay, so let me just write down what they call the Algamal Protocol. Okay. I think I have room here. Huh. Famous last words. Okay. So here's Bob over here. So Bob is only going to read messages, and Alice is only going to send messages. So in this protocol, Bob gets to pick the parameters. So he picks a large and probably a safe prime P. And then he also selects a generator alpha of ZP star. And then he computes his private key, which the book also calls D, kind of torn about whether or not to use extra notation, but just following what the book does here. So his private key is selected at random in the set 2 to P minus 2. So basically he's just picking a random element of the group, except that he's not dumb enough to pick 1, or he's not dumb enough to pick plus or minus 1. Okay, and so from that he computes his public key, which we're also calling beta, which is alpha to the D mod P. Okay, and then he needs to send all of this information to Alice so that she can communicate with him. So from Bob, Alice receives P and alpha. Those are just the parameters of the group. And then she also gets beta, which is basically Bob's public key. And so Bob never has to change his public key. It's going to be stable. But Alice does have to change things every time she sends a message because she wants to avoid repeating a key. So whenever she wants to send a message, so for each message, she chooses some I uniformly at random from the set 2 P minus 1. So this is 2 P minus 2. So she just picks some element of the group, but it's not plus or minus 1. And then she computes KE. So E here is for ephemeral. So this is going to be a secret that's used exactly one time. And this is alpha to the I. So this is just her Diffie-Hellman public key, mod P. And then she privately computes KM here, which is Bob's public key to her private key, mod P. And then she computes the current ciphertext, which is X times KM mod P. And then she sends KE, which is it's the ephemeral key, but it's also, in Diffie-Hellman terms, it's Alice's public key for this choice of I. And she also sends the message here. So notice that this expands the amount of data that Alice has to transmit by a factor of 2 here, because the ephemeral key is about the same number of bits as the message. So once Bob receives the ephemeral key, he computes KM, which is Alice's public key to his private key, mod P. So this is just the Diffie-Hellman shared secret. And then he computes X as Y times KM inverse mod P. Right, and there's a slick thing you can do here. It's actually possible to do these 2 steps at once. So I'm gonna show how that could work. So optimization for Bob here. So we know from Fermat's little theorem that any number, but in particular Alice's public key, the ephemeral key to the P minus 1 is congruent to 1 mod P. Okay, just reminding you of that fact. So Bob has to compute this inverse, which might be a pain. So to compute that inverse, he has to do Euclid's algorithm, right? Then he also has to do this modular exponentiation. So instead of doing those 2 steps it's possible for him to just do one modular exponentiation to get both Km and K. Well, he actually doesn't need Km, he just needs Km inverse. So what he's going to do is he's going to go right from the ephemeral key to Km inverse without pointlessly stopping at Km in between. So the way he can do that is, Km inverse is Ke to his private key D to the -1 mod P. And now I'm going to do an algebraic trick here, which is I'm going to multiply both sides of this equation by 1. But instead of writing 1, I'm going to write K to the P minus 1e. So I'm just multiplying both sides here by 1. So Km inverse is Ke to the D minus 1, but now times Ke to the P minus 1 mod P. And you can just put these exponents together, and Km inverse can also be expressed as Ke to the P minus D minus 1 mod P. All right, so this removes the needless intermediate stage. So all Bob has to do is one modular exponentiation and then one modular multiplication to recover x. Okay. So and Alice could also send a bunch of KEs ahead of time so that Bob could be pre-computing these things too if speed were really crucial. Okay. So I have a couple more things to say about Algamal Cipher. It has, we've already seen one problem, which is that the ephemeral key should not be reused. If anything, if you're using any kind of cryptographic system and something is called ephemeral, make sure you only use it once. I totally misspelled it here. Ephemeral key cannot be reused. That's KE, which is also Alice's public key. And Alice has to generate that for every message. So that's, how does she generate it? The expensive step is right there. And then she also has to compute Km. So she's doing two big modular exponentiations here is basically the price on Alice's side. So it's kind of twice as hard for Alice as it is for Bob, because he only has to do one big modular exponentiation. Okay. Another thing is that Algamal is subject to malleability, the same way that our school book RSA was. So our Algamal is vulnerable to malleability. Anybody remember what malleability means? So malleability means that Eve is here and she's watching a bunch of ciphertexts fly by. And if a cipher is malleable, Eve can intercept this Y, so she blocks it somehow, and she replaces it with some other adulterated ciphertext. But she does it in such a way that she can make a targeted change to the decryption. So for example, if Alice sends X encrypted as Y, Eve can make a change to Y that will make Bob think that the plain text was 2X instead of X. So she can make a targeted change to the decrypt. So that's not good. Let's see how that works. So it's you basically Eve replaces KE and Y. Remember, that's what she sees go by on the wire every time. This is what gets sent. So she's watching a bunch of those go by. And then she just, she replaces that with KESY, where she chooses S. So S is her choice.
But can she read the original Y?
No, she has no idea what it says. But
Yeah.
you know, if she knows that it's like a dollar amount, then she can double it or triple it or something like that.
Gotcha.
Okay. So then when it's time for Bob to decrypt this, so you know, Y is equal to KMX, and so SY is equal to S times KMX. And how does Bob decrypt? So Bob's decryption algorithm is to multiply whatever this is by the inverse of KM. So if he does that, then he applies KM inverse SY, and that turns out to be SX, because maybe I should write it all out. So this is KM inverse times S times KM times X, and so put these together and they kill each other, and it turns out to be SX. So if S were a 2, then Eve can you know, double what Bob thinks is the plaintext. So it's a malleability attack, kind of similar to the one that we did on RSA. The solution here is the same as the solution with RSA, and you have to use padding. So padding is sort of like applying like a keyless cipher to the plaintext before you encrypt it. So if that was the case, then this would be S times sort of the garbled mess. And then when Bob pulled it back through, the padding, the effect would be unpredictable to Eve because she doesn't know what X really is. And so from Eve's point of view, this will be gibberish. So she will still have forced the message to decrypt to gibberish, but she won't have any idea about any properties of that. You know, she can't make targeted change to it. Okay. And it's actually the end of my notes. I didn't think that we would get any further than that. So that's the end of chapter 8. And I guess we could say a little bit about digital signatures. But does anybody have any questions about what we just did? And so you should have some book problems on that, I think. So be sure to keep doing the book problems as we go along here, because I am going to grade the book problems or check that you did them. I've seen the work of some people and it's really good. So I think can I show you guys the textbook without getting in trouble? Okay. So are you guys looking at this now? I don't think so. Sorry. So the next chapter of the book is elliptic curves. But we're not going to talk about elliptic curves. And so after elliptic curves are digital signatures. So we'll go right to digital signatures. So let me just tell you a little bit about digital signatures. So a signature in real life, what kind of properties does a signature provide? It's like an identity mechanism, right?
Yeah, like security.
Yeah, so my signature sort of is me as far as like documents are concerned. So if my signature is on a document, it means that I approve the document. And this is like our half medieval, like pitiful pre-technological or half technological society's version of non-repudiability. So if I sign something, then if I sign a check, then the idea anyway is that I can't later say that I didn't sign the check. If I write Gibran a check for $100 and I sign it, then if I change my mind later, Gibran can say, look, you know, your signature is on the check or on the contract or something. So it's a way to stop me from trying to weasel out of something. And so digital signatures can serve a similar purpose. So this is a public key thing. And so, you know, in public key cryptography, everybody has a private key. So in order to sign a document, we use our private keys. So the idea is that each one of us has a private key that nobody ever gets to see. And from the point of view of documents and stuff, our signature kind of is us. And anything that we apply our private key to, so you need this for signing. So this allows us to sign. And then later, people will want to verify our signature on various documents. And in order to verify our signature, you use the public key. So this is for signature verification. So you can do a really simple example of this just with RSA. It's almost the same as just the RSA encryption. So remember with the Rsa Cipher, you have a public key, which is, I think we were using lowercase n and e, and n is equal to p times q. This is the public key. And there's also some private key d, which you know, only you know in this situation. And so suppose we want to sign X. Then you just do X to the D is your signature. So S equals X to the D mod n. And so, you know, signing something is separate from keeping it private. So in some cases, you might want to just send the document unencrypted together with your signature over to somebody, you know, like, so here's a contract. So I send both the contract and my signature. And so then the receiver wants to verify the signature. So how can that be done? So the receiver can do S to the E, because everybody gets to see E and N. So S to the E is X to the DE. And just like with RSA encryption, this is the same thing as X mod N. So the receiver just asks, you know, is SE congruent to X mod N? And if the answer is yes, then the signature is valid. And if the answer is no, then the signature is invalid. Okay. And so digital signatures, you know, can be used for a lot of stuff. Like, you know, one thing that irritates me to no end, and this is like, probably you guys have been dealing with this with the coronavirus and stuff. Like, if I want to use my credit card to buy a pizza, then I can call the pizzeria, but in order to pay them, I have to tell them my credit card number. So, and in order to let them charge my credit card, I have to give them the secret that they need to know in order to spend my money. You know, like, then why don't they call some other pizzeria and tell that pizzeria my credit card number and all that stuff that I just told them, and, you know, order the pizza from them. I don't know. So it just annoys me that you can't use your credit card without giving up your credit card number. But with digital signatures, that's really not necessary anymore. And I guess eventually society will get around, when people care enough or something terrible enough happens, to make it so that you're basically, you can use a digital signature to approve something without giving other people the ability to approve it. You know, like I can write down an order for a pizza, and then I can digitally sign it, and then the pizzeria can show that signed document to my bank, and my bank can then pay them, you know, whatever, $20. But they can't then go on to like use that to buy other pizzas or something. You know, it's so, I don't know. So digital signatures. So I'm just kind of winging it here because I really didn't think we would get this far, but I guess I have to keep tap dancing here for like 7 more minutes. So can I just maybe say some other applications? Like cryptocurrency is based on digital signatures. The cryptocurrency Bitcoin anyway uses a signature scheme called elliptic curve DSA. DSA stands for digital signature algorithm, and this is a variant on the Algamal signature system, which we will probably eventually talk about. And like in Bitcoin or Ethereum or something, it's sort of like that pizza example I just described, except and there's no bank involved. So if I wanted to pay Nikita like 1 Bitcoin or something, then I just I digitally sign a statement that basically says one of my Bitcoins now belongs to Nikita, and then I put that on the Bitcoin blockchain, and you know, putting aside for the moment like how how everybody knows that the Bitcoin blockchain is like an authentic record of real transactions. But assuming that you've solved that problem, then anybody can look at the Bitcoin blockchain and they see like, oh, Hunter credited Nikita with 1 of his Bitcoins. So Hunter has 1 Bitcoin less and Nikita has 1 Bitcoin more. And so you don't need like some kind of centralized balance sheet at a bank. You have a public balance sheet in the form of a blockchain, which is really cool. And then there's the problem of how everybody agrees on what the Bitcoin blockchain actually says, you know, and that has to do with something called proof of work that also is a cryptographic idea, and it basically has to do with repeated hashing, but we haven't talked about that. What do you guys think about cryptocurrency? So it's nice that we can have these public ledgers. I mean, they have lots of applications like what I just described, but then they also have like downsides. One of them is that they use a lot. Proof of work uses a lot of energy. Like it uses the Bitcoin blockchain uses as much energy as like Ireland. I think the last time I checked, if it hasn't gone down. And people use them for things. I mean, cryptocurrency has made like ransomware attacks possible. So whereas it wasn't really possible to do a ransomware attack before. But on the other hand, it has like it has some benefits too. You guys, would you say you have a favorable or unfavorable opinion?
I mean, for me, it's just like it is what it is because we can't really avoid that. You know, like we have to go ahead.
Yeah, because whatever you feel about it, you know, eventually you guys will be the adults. Like, you know, you'll be the old people in Congress who make the laws, and if people in your generation like, you know, like cryptocurrency or like whatever, you know, however much it is despised now, then it could, you know, become more widely accepted.
I feel like online banking isn't going to go anywhere anytime soon. So it kind of makes sense.
Online banking works well, you know, like I feel I mean, like switching, if you want to just switch to Bitcoin, like they make it a a pain because you have to pay taxes on every single transaction. Like if you spend like $1, then you have to put that on your tax returns. And so it's a pain. It's a pain to use Bitcoin. It's complicated, and banking works pretty well. If there was like a run on banks or something like that, I mean, some pretty crazy financial stuff is happening right now. But basically, you know, the people who manage the dollar have been doing a decent job. So I don't know. Okay, so let me just take attendance really fast. We're getting toward the end of the semester. It's like kind of amazing. So is Shipu here? I better stop.
Yes, Professor. Yes, Professor.
Okay, thank you. I'm gonna stop recording.